Okay, so power series defines a function. So a power series f of x, that's our function. You can just imagine any function. I mean, usually like, let's say sine of x, cosine of x, tangent of x, or natural logarithm of x. These functions. So these are, what is it? Power series representation of these functions. Okay. So whose domain is the interval of convergence of series? Because in that interval, if we just pick any point and evaluate this power series, it gives us the approximate value of this function at this point. Right? Otherwise, if you just pick any point that does not belong to the interval of convergence, then that approximation does not work here. So if the radius of convergence, if r is positive or is equal to positive infinity, what does it mean? That means that r equals positive infinity means at every value of x on the number line, right? If we just substitute here and evaluate this, actually gives us the approximate value of this f. If we just pick a finite number of terms of this power series. All right. So moreover, f prime and the integral of f can be found by term differentiation and integration. Convergence at an endpoint may be either lost by differentiation or gained through integration. Okay, and the things again you learn in calculus. This is what we have to know, and through the examples, when I just do this, you will see that it is not so complicated. Okay, because differentiating this power series means differentiating a polynomial function, right? Integrating a power series means integrating again polynomial function. The only difference is in series it has infinitely many terms. For example, write down the first and second order derivatives of this function. Assume that here we have a kind of function that is f of x, and assume that this is the power series representation of this function. Okay, that is equal to, if you just expand this, here we have c sub 0 plus c sub 1x plus c sub 2 x squared plus c sub 3 x cubed, blah blah blah. It goes to positive infinity, right? So now if I differentiate this here, what is y prime? So I need to differentiate each term, right? One by one. So that is a constant that's equal to 0, right? So here we have, if we differentiate this, for example, let me just write here, y prime is equal to this thing is equal to 0. This thing, right, that's equal to c sub 1. This thing, it is 2c sub 2x, right? Plus this thing 3c sub 3 x squared, because 3 minus 2 and 3 minus 1, and continuous. We don't have to write all the terms. I mean, just 3-4 terms is enough. So here we have c sub 1 plus 2c sub 2x plus 3c sub 3x squared plus blah blah. And also, if I just write this in compact form using the sigma notation, right, what we have here, as you see the difference here, they match each other, right? And that's why here we have n c sub n. But here, the power of exponent of this x is 1 less than this subscript notation, right? So that is n minus 1. So here, since the first one is 1, so n starts with 1. This index starts with 1. Okay, but if we want to write here n, what should we write here? At that time, if you want to write here n, so this index, also I can just write it, we call this shifting the index, right? I can just write here, let's say n is equal to 0 to positive infinity. I can write here n plus 1 times c sub n plus 1 times x to the power n. And also they are the same thing exactly, only here the index is different, right? And we call this operation shifting the index of the sigma notation, or the sigma. Here it starts with 1, here it starts with 0. And also here this expression is different, right? Here we have n times c sub n times x to the power n minus 1. But here we have n plus 1, cn plus 1, x to the power n. But actually they represent exactly the same thing. If we just expand this, right, that is the expansion of this one. These two things are exactly the same things. And how about the second order derivative? So this one is y prime. Now I need to differentiate this one more time, right, to get the second order derivative of this power series. So here we have y double prime, and it's already 0. And also it's a constant, is also equal to 0, right? If you differentiate this, here we have c sub 2. If you differentiate this, here we have 6 c sub 3 x c sub 3 x, right? And continue. Next one will be maybe 12 something or 18, right? So here 0 0. Now it starts with 2, right? Because the smallest index here is 2 here, the constant. So here it starts with the n equals 2 to pause to infinity. So here we have 2 6 something, right? So here we have 2 2. So that is n minus 1, because the previous one is this n just comes to the front, n times n minus 1. That's a general term, right? Here we have c sub n times n minus 1. But now here we have x to the power n minus 2. Right? If you just write a few terms here, if n equals 2, that's equal to 1, that's equal to 0. So here we have c, 2 times c sub 2. If n equals 3, we get the second term. If n equals 3 or 4, we get the third term, right? And blah, blah, blah. And this is how we integrate, differentiate power series. And also if you want to, for example, if we want to get this y, for example, how can we get y? I need to integrate both sides, right? And also we know how to integrate polynomial function. Okay, and this is about differentiating and integrating power series. Next thing is, this is a very important thing to solve our differential equation and to identify the coefficients identity property. Okay, in math, you know that when we say identity, we mean a special equation, right? Because it has equal sign. Usually all the formulas, they are examples for identities, right? When we just say identity, for example, let's say this P of X is identically equal to Q of X. What does it mean? It means that for every value of X in the interval of definition here, this P is equal to Q. It means this. But if it is equation, it's not like this, right? First we have to solve this. Only the solution satisfy this one. But when we say that they are identically equal to each other for every value of X, this left-hand side should be equal to right-hand side. Okay. For example, if we are given something like this, a sub 2 x squared plus a sub 1 x plus a sub 0 is equal to x plus 1. Now, if this one is identity, how can we identify or determine this a sub 2, a sub 1, a sub 0? Here we have x plus 1, right? So that means that their corresponding coefficients must be equal to each other. What I have here is, here we have a sub 2 x squared plus a sub 1 x plus a sub 2. On the right hand side, I have 0 times x squared plus 1 times x plus 1, right? So that means that this x sub 2 must be equal to 0 if these two things are identically equal to each other. So this a sub 1, it should be equal to 1. And this a sub 0, it should be equal to 1, right? Okay. And in solving differential equations, this homogeneous differential equations, on the right-hand side, we have 0. We assume that this is a solution of the differential equation and substitute there, differentiate once or twice and simplify this. On the right-hand side, we have 0. Actually, this 0 doesn't mean that it's an equation. Actually, it means that that is identically equal to 0. That means that for polynomial, when actually polynomial is equal to 0, or what is 0 polynomial? 0 polynomial is the one where all the coefficients are is equal to 0. right? All the coefficients must be equal to 0. Then we call this a zero polynomial. Analytic at the points, another concept here. A function f is said to be analytic at a point a if it can be represented by a power series in x minus a with either a positive or an infinite radius of convergence. Okay, simply if you're given a function, if we can express this as a power series representation, or if we can find it is power series representation, then we say that the given function is analytic at a point A, because here we are using this A, right? That's the center of convergence. All right, guys, do you have any questions? You're so quiet. Okay. So some series, as you know that also you studied this, you must have studied in Calculus 3, Taylor series and Maclaurin series. Okay. So if you're talking about a function which is infinitely many times differentiable, okay, these functions, like we can expand them to Taylor series. How? That f of x, that is equal to, and also actually we get this from the power series, here nth order derivative of f of a over n factorial times x minus a to the power n. If we just expand it, what we have here, f of a plus f prime of a over 1 factorial x minus a, blah blah blah. That is Taylor series, okay, of what? This f of x. This Maclaurin series is just the special case of this Taylor series. If a is equal to 0, that means that we are just expanding this at 0. Okay, that is equal to, this should be 0, not a, that is 0. Let me just change this immediately there. Only at 0. Okay, that is f of 0 plus f prime of 0 over 1 factorial times x and blah blah blah. Okay, and using this we can write some power series representation of these functions. The first one is e to the power x, for example. Just we know how to evaluate this one at 0. Differentiate this and evaluate 0, substitute here. Differentiate twice, substitute here. We know that for e to the power x, right? If our this thing is, if our f of x is equal to e to the power x, and what is, it is nth order derivative of this function. We know that if you differentiate infinite many times, it does not change, right? So is equal to e to the power x. And any order derivative of this function at 0, that's equal to e to the power 0, which is equal to 1. So that is exactly the same thing, but here we have 1 over 1 factorial x, 1 over this x squared, and 1 3 factorial x cubed. And that's why here we have the Maclaurin series representation of e to the power x is equal to this. Okay, how we are obtaining this? 1 plus x over 1 factorial plus x squared over 2 factorial and blah blah. In compact notation, by using sigma notation, we can express this way. And what is actually the convergence, interval of convergence? So this thing, right, if we just evaluate this, okay, x to the power n plus 1 over x, and evaluate this, you will see that actually, for example here, this x to the power n plus 1 over n plus 1 times, actually divided, right? Here we have absolute value. Here we have n over x to the power n. Using the ratio test and finding the interval convergence. If you evaluate this, these two cancels each other. Here we have x times, right? And this thing is n over n plus 1, right? and this will approach, what is it? This x. Is it x or all right? This x n plus 1. Factorial, sorry. Here we have n plus 1 factorial, and here we have n factorial, right? And here we have factorial, and here we have factorial. Okay. So we know that this n plus 1 factorial, it is n factorial times n plus 1. So here we have absolute value of x times 1 over n plus 1. And when n goes to positive infinity, right, this will approach to what? It will approach to 0 for every value of x, because a constant number, if you just substitute anything, and here we have n plus 1 is going to positive infinity. It's always 0. And 0 is always less than 1. That means that for every value of x, this one is convergent. And that's why the interval of convergence is from minus infinity to infinity. Okay? That is Maclaurin series representation of e to the power x. How about cosine of x? In similar way, you can differentiate 1 time, 2 times, 3 times to write this terms 4 times and evaluate at 0, okay? And substitute here, you will get this power series representation of this cosine of x. That's equal to 1 minus x squared over 2 factorial plus x to the power 4 and blah, blah, blah. In compact representation, notation is this. And also for every value, it is convergent. You can just use ratio test and you can show this. Okay, boys, again, what we are doing here is, for example, if you want to evaluate the value of cosine of x, okay, or e to the power x, let's say e to the power 3, for example, or 1.2. If you just take, for example, 10 terms, it will give you very close approximation of this e to the power, let's say 1.2. And on the right hand side, we have just polynomial function, right? And just multiply and divide something that is defined in every computer. All right, here evaluating e to the power x, evaluating polynomial, it is much easier than this. Anyway, we have to define this one, right? How do you define this in computer? So the only way to approximate is using this Maclaurin series representation. So anyway, in similar way, it's the sine of x, it is equal to this, okay, by using, again, this Taylor series differentiate this. At 0 is Maclaurin series. We can write it is representation in this way, okay? And tangent inverse, and here we have cosh, right? Here we have sinh, and natural logarithm of 1 plus x is equal to this, and 1 minus x also that's equal to this. That is just geometric progression, okay? We may just get this thing, how we are obtaining this one, and this thing is our f of x. All right, just differentiate this thing and you will get the function. Another way also is, it's just, what is this? Geometric progression, and that's equal to 1 over 1 minus x, and also you can get it is sum. Anyway, guys, here, these are just some examples. Again, these are from calculus, and you have to be familiar with some of them, especially like what is e to the power x, cosine of x, sine of x, okay? Because when you solve this, your power series solution is, let's say, this. So now, if I know that that is equal to e to the power x, I don't have to write this thing, right? So I can just write e to the power x. Now you'll see them in example. So arithmetic power series. Also arithmetic power series, if you're given 2 power series, we can add them, right? We can subtract them, and we can multiply them together, and we can divide 1 power series by another one. How? It's very similar, almost exactly the same with all the operations on polynomials. And polynomials, we need to just add or subtract their like terms, right? And in multiplication, multiply 1 term by every term, and a second term by every term. In this way, we can obtain. For example, here, assume that we need to multiply e to the power x times sine of x, right? And what is e to the power x? What is the power series representation of e to the power x? It is this, 1 plus x over 1 factorial plus x squared and blah, blah. And how about sine of x? That's equal to this. In the previous slide, we have seen that, right? X minus x cubed over 3 factorial plus x to the power 5 over 5 factorial, blah, blah, blah. Now to multiply this one first, I multiply this by all the things that has x, because first, if I want to write this in ascending order, right, first I need to write constant. As you see here, we have x, right, so we don't have constant term here, and the first degree of x, right, that is just x. So to get this x to the power 1, I should multiply this term by this. That is x to the power 1, so that is 1 times x. Now, how about x squared? To get x squared, we don't have x squared here. I cannot get x squared multiply 1 by anything here. So the only way to get x squared is I should multiply this term by this, right? So here we have x, here we have 1, and x, that is x squared, right? And how about x cubed? To get x cubed, I should multiply 1 by this, right? That is minus 1 over 6. Or I should multiply x squared by this, right? Only the product gives us x cubed. So that is 1 over 2 times 1, that's 1 over 2, x cubed. In this way, we will continue. How about x to the power 4? So by multiplying any term by 1, I cannot get x to the power 4, but multiplying this x by x cubed, we can get this, that is minus 1 over 6 because of this minus. And also multiplying this, what is it? X to the power 4, this x squared, yes, this x cubed, x, right? That gives us x to the power 4. And also this x and the x cubed, right? It gives us x to the power 4. All right. And in this way, we can just continue this and simplify this. We will get x plus x squared plus x cubed over 3 minus x to the power of over 30 plus blah, blah, blah. We can just write 4 or 5 terms. That would be enough. And this is how we multiply two power series together. Okay? Shifting the summation index. For the 3 remaining sections of this chapter, it is crucial that you become adept at simplifying the sum of 2 or more power series. Each series expressed in summation notation to an expression with a single sigma notation. As the next example illustrates, combining 2 or more summations as a single summation often requires a re-indexing. That is a shift in the index of summation. Okay? Because usually if you are solving differential equation and we are looking for this power series solution, and when you solve this, you may have, maybe you will see that in the next example, you will see that we assume that power series solution is given, and to determine its coefficients, mainly we have to determine it is coefficients, right? This C sub n's. So I have to put into the equation, and after that we have to express as a single power series. Then we can determine the values of C sub n. Okay, here first let's just focus on this example. We are given two power series right here. How can I combine them? How can we add them together? Or how can I express this using a single sigma notation? To do this one, actually we have to re-index this, right? So here we have this n is starting with 0, and here n is starting with 2. All right. And let's say I'm going to write here as a single sigma notation. And here I'm going to write, actually it's up to you. You may want your index to start with 0 or 1 or 2. Let's say I wanted to start with 1. K is equal to 1 to positive infinity, right? And here we have x, here we have x something. So here we have something like that. I'm going to write this, C sub k times x to the power something. Maybe it may be different, just giving you some example, okay? Because here this the thing may be different. Anyway, we are just going to write this as a single index. To do this one, what is the first step? How can I write this? I mean, how can I make this start with 1? Okay, because it is starting with 2, right? The first one, for example, I can just write it as sigma n equals 2 to positive infinity. Here we have n minus 1, c sub n, x to the power n minus 2, right? So instead of here n equals, let's say, if I write n equals not n equals, okay. All right. So that's equal to, let me just write here, k equals 1 to positive infinity, right? So when n equals 2, here we have 2, right? So here when k equals 1, I need to have 2 here. So what should we write here? To have 2 here, this should be k plus 1, right? And here we have when n equals 2, that's equal to 1. Actually, this thing is 1 less than this. So here I need to have k, right? This k is 1 less than this. So here we have c, right? And here we have k. When n equals 2, this is equal to 2. So this starting with 2. So when k equals 1, it should be k plus 1. As you see here, the first term is when k equals 1, it is 2. Here we have 1 times 2. So here we have 1 times 2. Times x to the power, x to the power. What do we have here? When n equals 2 is equal to 0. So to get 0 here, when k equals 1, so here we should have k minus 1, right? When k equals 1 is equal to 0. If k equals 2, it is 1. If k equals 3, it is 1, the second term, right? I just shifted 1 back. The second one is, here we have sigma n is equal to 0 to positive infinity. Here we have c sub n times x to the power n plus 1, right? Again, if I just write this in a similar way, let's say it starts with 1. K equals 1 to positive infinity, right? So here we have c sub n. When it is 0 is equal to 0, right? But now, when k equals 1, if we want this to be 0, this should be k minus 1, right? And here 1 is equal to 0, it's equal to 1. So here we have x to the power k, right? The first term is here, when k equals 1, c sub 0, x. Here we have 1 is 0, it is c sub 0, x, right? Now here, sigma notation, k equals 1, k equals 1, everything is the same, right? So let me just write this thing, I mean, just a, okay. Now, what is a? A is this plus this. And what is this is equal to this, right? So I can just write a single sigma notation. K equals 1 to positive infinity because it's a common thing. First write this one. That's equal to k plus 1 times c sub k plus 1 times x to the power k minus 1, right? And the plus, here we have c sub k minus 1, c sub k minus 1 times x to the power k. Okay. All right. So here we have x to the power k minus 1. Here we have x to the power k. I cannot take this out. So how can I re-index this? So that's yeah, because this power of x should be the same. Here we have k minus 1. Here we have k. So it is k. Oh, but if I want to have k minus 1 here? All right. All right, to do this one, because I want to write this x to the power k outside, right? So here we have x to the power k minus 1, x to the power k. What can I do here? Because it's starting when it's 1, starting with 1, it's starting with 0, right? So to do this one, yeah, this one, let me just rewrite this one, okay? So we can just write it as when it is 0, c sub 0, x to the power 1. So it is c sub 0 x. Okay, c sub 0 x, but here it is 2. All right. Okay. So I think we better do this here because here every term has x, we have nothing to do here. N equals or k is equal to 1 to positive infinity. C, k minus 1. X the power when it's 0 is 1, so it is k, right? But this thing, I think we can make some adjustments that is equal to, when k is equal to 1, here we have 1, here we have 2, here we have 2, right? 2 c sub 2, right? 1 is equal to 1 is equal to 0 plus, I can just write it as sigma k equals 2 because this the first term is here, the positive infinity. Here we have k plus 1, c sub k plus 1, x to the power k minus 1. Okay. So this is the main point actually here because we don't have the same thing here. I want to keep this outside here. Here we have only the coefficients, okay? To do this one, now I need to shift because here this is starting with 2, right? This is starting with 2, but here it is starting with 1. So I just need to shift this to the left. To do this one, here we have 2 c sub 2 equals, here we have 2, 3, right? If k starts with 1, right? So here it is 2, 3. It should be here. I should just add 1 to this. So here we have k plus 1, k plus 2, right? If it is 1 here, we have 2 times 3. If it is 2, 2 times 3, the same thing. And here, when k equals 2 is equal to 3, right? When k equals 1, it should be 3. So here we have c k plus 2. Now here, when it is 2 is equal to 1. When it is 1, it should be x. So here we have x to the power k. Okay, now here we have x to the power k. Here we have x to the power k. And starting with 1, it's starting with 1. Now if I add this, first I need to write this outside. Here we have 2 c sub 2 plus sigma, okay, k equals 1 to positive infinity. Here we have x to the power k. X to the power k is a common factor. Here we have c sub k minus 1 plus, here we have k plus 1, k plus 2, c sub k plus 2, and here we have x to the power k. Okay. Gentlemen, maybe it may be a bit messy. Maybe I will re-record and share with you in a more organized way. And the main idea is, as you see, here we have two sigma notations. We need to combine them. When we combine them, the powers of x, it should be the same. Then I can take this out. Okay, here we need to have only that numbers, constant numbers, or these coefficients, okay? So that when I am equating with something or zero, I will just consider that this is equal to zero. Then I can find the relationship between these coefficients, okay? When we solve that example, you will understand much better, okay? I will resolve this and share with you, because now we have only around 2 minutes left. About some other problems, when I just saw in this way, you know, as you see in power series solution, it's going to take a lot of time. I think I'm going to solve earlier, okay, and after that I share with you, and also we have some discussion about this, and this is how we continue from today, okay? But thank you very much. If you have any questions or if you are stuck with any problem, you can just let me know. Either I will explain again or I will make a video and share with you on YouTube. Okay, that is enough for today. Thank you very much.
Sir,
yes.
Excuse me, sir.
Yes.
Again,
Yes.
like the presentation will taken in the class on the class time or like after 20, like out of class time.
Yeah, presentation will not be during the class time. Okay, class time only I will teach because we don't have much time.
I see.
So you should tell me, Mr. Qasim, during this time I can present, okay? Like in the afternoon, any day is fine because I'll be available. And I suggest you to do your presentation between 1 and 3. Okay, anytime, like if you have 15 minutes break, let's say, Mr. Qasim, can I do my presentation between 1:30 and 1:45? It's okay. But we will need 20 minutes because 5 minutes for connection and opening everything, okay?
Okay, sir.
Okay, guys, now it's going to close because only about 1 minute left. If more questions, please write it in Telegram, okay? See you next time. Bye-bye.